Hi, today we will discuss deflections using energy methods, specifically the virtual world method. As an overview, I will give you a short introduction, then talk about the conservation of energy principle as used in the work and the conservation of energy principle. Then we go towards the virtual work or the complementary virtual work method. Then we apply the virtual work in truss deflections. In our discussion, it can be shown that the deflections and angle changes may be determined using the principle of conservation of energy. Only one of the common energy methods, that is the virtual work, which will be discussed. Virtual work can be used for both simple and complicated structures. In addition, the energy methods are applicable to more types of structures. But before going through, we need to define the concept of work, especially for a constant force. Work is defined as a product of the force and its displacement in the direction in which the force is acting. If the force be constant during the displacement, the work will equal the force times the total displacement, as shown in the diagram on the right. W is equal to P times delta, the area of the green space. But on many practical occasions, the force changes in magnitude as does the deformation. So for such situations, it is necessary to compute the area under the force deformation plot. Is a triangular area, or actually we have a straight line. The force versus the deformation is a straight line. So this can be done mathematically by summing up the small increments of work for which the force is assumed to be constant. If a linear relationship exists between the force and the displacement as shown here, then we can actually use the integral function. The integral is, or the work is equal to the integral of the force P times delta d delta, which is equal to 1/2 of P delta. So this is the area of the triangle. Again, you have to compare it with the constant force. The area is the rectangular area, P delta. But for a force that changes in magnitude, like this one, then the work is simply equal to 1/2 of P times delta. Note that the conservation of energy principle is the basis of all energy methods when a set of external loads is applied to a deformable structure. The points of load application move with the result that the members or elements making up the structure become deformed. According to the conservation of energy principle, the work done by the external loads, that's W sub E, equals the work done by the internal forces acting in the elements of the structure, denoted as W sub I. Stated mathematically, this principle takes the form W sub E is equal to W sub I. As the deformation of a structure takes place, the internal work, which is also referred to as the strain energy, is stored within the structure as a potential energy. If the elastic limit of the material is not exceeded, the elastic strain energy will be sufficient to return the structure to its original undeformed state when the loads are removed. If a structure is subjected to more than one load, total energy stored in the body will equal the sum of the energies stored in the structure by each of the loads. Note that the conservation of energy principle will be applicable only, take note, applicable only when static loads are applied to elastic system. Static loads applied to the elastic systems. If the loads are not applied gradually, acceleration may occur and some of the external load will be transferred into kinetic energy. If inelastic strains are present, some of the energy will be lost in the form of, among other things. With the virtual work principle, a system of forces in equilibrium is related to a compatible system of displacements in a structure. The virtual quantities discussed here do not exist in real sense. When we speak of a virtual displacement, we are speaking of a fictitious displacement imposed on a structure. The work performed by a set of real forces during a virtual displacement is called virtual work. So for its virtual work theorem, there is a corresponding theorem that is based on complementary virtual work. As a result, this method is sometimes referred to as complementary virtual work. Virtual work is based on the principle of virtual velocities, which was introduced by Johann Bernoulli of Switzerland in 1717. It can be stated, or the virtual work theorem can be stated this way. If a displacement is applied to a deformable body that is in equilibrium under a known load or loads, the external work performed by the existing load or loads due to this new displacement will equal the internal work performed by the stresses existing in the body that were caused by the original load or loads. Note that the virtual work or complementary work method is also referred to as the method of work or the dummy unit load method. The name dummy unit load method is given because a fictitious or a dummy unit load is used in the solution. But before going through, we need to know some assumptions of the virtual work. Note that virtual work is based on the law of conservation of energy. To make use of this law in the derivation to follow, it is necessary to make the following assumptions. You have to remember these three assumptions. The external and internal forces are in equilibrium. Second, the elastic limit of the material is not exceeded. And third, there is no movement of the supports. Let a load P sub 1 be gradually applied to the bar as shown. Gradually applied, so we can assume it to be static load. Actually, if you just apply it directly, it will become static dynamic load. But since we apply P sub 1 gradually, then the load and the bar's deformation or the change in length increase together from 0 to their total values. So we have P1 if you have to apply the load gradually, and it will give us the maximum displacement of delta 1. The external work done will equal the area or region 1 on the figure under the force displacement curve as shown. So this area of the figure is simply equal to the area of a triangle. That is, the external work W sub E is 1/2 of P1 times delta 1. Remember, the force P is real force. We apply the real force times, then it will give us the real displacement delta 1. Let another gradually applied force P sub 2 be added to the bar. So aside from P sub 1, we will gradually add the force P sub 2, causing an additional displacement delta 2. This causes additional external work to occur, as you can see in the figure. Note that the force P1 will be entirely present for all of the delta 2 displacement, and the work associated with that will be P1 delta 2. Look at this one, the yellow region. We have the height P1 and the width delta 2. So that's why the force in this region 2 is P1 delta 2, which is represented by yellow. The gradually applied force P sub 2 will perform an additional amount of work equal to the region 3. So aside from region 1, region 2, we also have region 3, which is equal to the area of the triangle, 1/2 times the height, that is P2, times the width, delta 2. Therefore, the total external work done by both forces, that is P1 and P2, is equal to this lower triangle, region 1, region 2, and region 3. So W sub A is simply equal to the region 1, 1/2 P1 delta 1 plus region 2 P1 delta 2 plus region 3 1/2 P2 delta 2. If the load P1 is a real load, P2 is a virtual load, then the following interpretations can be made with this diagram. For the region 1, the work done by the real load, that's P1, acting over the real displacement delta 1. In region 2, it is the work done by the real load P1 acting over a virtual displacement delta 2. The region 3 is the work done by the virtual load P sub 2 acting over a virtual displacement delta 2. Region 4 is that the work done by the virtual work P2 acting over the real displacement delta 1. Here, the expression for the external work represents the total area beneath the slope line in the figure. Another type of work is known as complementary work, W asterisk. What is this? This is represented by the total area above the curve. So if we have this virtual work, blue, yellow, and red, the complementary work is the opposite, this one, this two triangles and region 4. One may readily deduce then that its region 1, 2, 3 has an equal counterpart, has an equal counterpart. For example, the area, that is the work in region 2, this one, is equal to the complementary work in region 4. So this region 2 is equal to region 4. The complementary work does not really have a physical meaning, as does the external work W sub E, but it can provide a convenient way of looking at deflections in structures. From the previous slide, the work represented in region 4, this one, can be called the virtual external work, that is delta W sub E, since it is the work done by a virtual load P sub 2 acting over the real displacement delta 1. Here, the objective of the virtual work approach is to solve for the unknown real displacement, that is delta 1, in a structure. Therefore, this description of the virtual work term delta W sub E is used hereafter. Then we can also apply this concept, the virtual work concept, in truss deflections. The conservation of energy principle says that the external work must be equal to the internal work or the strain energy. The same thing could be said about virtual work. Such an interpretation would be delta W sub E asterisk is equal to delta W sub I asterisk, which is equal to P sub 2 delta 1, which is equal to delta W sub I asterisk. This relationship states that if a virtual load is applied to a structure and the internal virtual strain energy is computed, the deflection in the structure can be directly determined. Thus, the focus here will be on deriving the strain energy term for a truss bar axial member and using it to calculate deflections in trusses. So now we will derive the internal virtual strain energy using the same concept we have done in the external work. The internal strain energy is easily derived in the same fashion that the external work was derived. You can see in this diagram, we have the same diagram but with different parameters. The figure shows the same sequence of loading as was described from the previous figure. The only difference is that the force deformation plot is written in terms of the internal axial forces N and capital N and small n instead of the external forces P1 and P2. This external or internal axial forces N, capital N and small n is also in terms of sigma and the cross-sectional area and the epsilon and length of the bar respectively. As you can see, capital N is the internal axial force in the member due to the applied real load P sub 1, and small n is the internal axial force in the member due to the applied virtual load P sub 2. Take note, we will be using Hooke's law here, which is defined as sigma is equal to E times epsilon. Also, stress is defined as the force over the area, or the normal force N over the cross-sectional area A. That's sigma 1. But for sigma 2, we can also use the same notation, the same meaning, but the internal axial force due to the applied virtual load, that's small n over the cross-sectional area. Also, the strain or the epsilon 1 is equal to delta 1 over L and epsilon 2 is delta 2 over L. We will be using this one in our derivation. Using Hooke's law in conjunction with the well-known mechanics equations for stress, that is sigma is equal to N over A, and strain, that is epsilon is equal to delta over L in an axial bar. The internal work equation can be written as W sub I is region 1 plus region 2 plus region 3. Here, the region 1 is the area of the blue triangle, that is 1/2 of sigma 1 times A times epsilon 1 times L here, this area, plus the area occupied by the orange region or region 2, the height is sigma 1 times A, base is equal to epsilon 2 times L, plus the region 3, the green one, which is the area of the triangle, 1/2 of the height, which is sigma 2 times A, times the base, which is equal to epsilon 2 times L. This would mean that the complementary virtual strain energy represented by region 4 is given as this one, region 2. So delta Wi asterisk is equal to region 2. That's a sigma 2a times epsilon 1 times L. If we back substitute expressions for sigma A and the Hooke's law, the expression can further be modified into the following form. Delta Wi asterisk is equal to sigma 2 is n or small n over A. Sorry for this bottom notation. Sigma 2 is n over A, not n. This is due to the virtual stress. And times A, and epsilon 1 is equal to sigma 1 over E, where sigma 1 is n over A over E. So in this way, sigma 1 over E, and then sigma 1 is n over A over E. We can actually factor out A, and the remaining terms will be small n, capital N, L over E. So the internal work delta Wi asterisk is simply equal to small n, capital N, L over E. With an expression for the internal virtual strain energy in hand, the conservation of energy principle may be used to complete the virtual work method for trusses. The derivation of the internal strain energy was done for single truss member. However, it is readily applied to an entire truss by considering the strain energy in all truss members. This is done by summing up all the effects. That is, external work, delta W sub E, is simply equal to the internal work, that is delta W sub I, where the external work is P sub 2 delta 1. P sub 2 is the virtual load times the real displacement delta 1, which is equal to the summation of all the members of the truss, Ni, Li over Ei. That is for all the members of the truss, where of course the subscript I denotes the truss member, and capital N, small n, La, and E are the real bar force, virtual force, bar length, bar cross-sectional area, and modulus of elasticity, respectively. So we can now use this formula to compute the displacement or deflection of a truss. Of course, you can use any values of P sub 2, the virtual load, but most often we assume P sub 2 equal to 1.0 for AC computation. So that is why the formula here to be used for the computation of deflections of a truss is delta 1 is equal to the summation of Li over Ei divided by 1.0. That is for all the members. Here is the procedure in using the virtual work to trusses. Procedure 1, calculate the internal axial force in every member of the truss due to the real loads applied on the truss. We call it N sub I. Remove all of the real loads from the truss and place a unit virtual load 1.0 at the joint and in the direction of the desired deflection. Take note, it should be in the direction of the desired deflection. Calculate the axial force in every member due to the applied virtual load Ni. Then use the equation of virtual work to calculate the deflection. So here is an example taken from NIELSON and MCCORMAC. Use the method of virtual work to determine the horizontal and vertical components of deflection at joint E in the truss below. The cross-sectional areas for each bar are given. That is, all horizontal bars 4 2.0 n square, all vertical bars 2.0 n square, all diagonal bars 3.0 n square, and the modulus of elasticity is 29,000 KSI. So for our solution strategy, analyze the truss for the given loads using the method of joins. This is done because every truss force must be known. Do this for the real, that is actual, and the virtual loads following the procedure as outlined previously. Use a table to make computations easier. A spreadsheet is handy. The modulus of elasticity is carried through as a constant until the summation is made for all of the members, at which time its numerical value is used. Should there be members of different E values, it is necessary that their actual or the relative values be used for the individual multiplications. A positive value of the summation of n and L over I indicates a deflection in the direction of the unit load. Excuse me. Here is the solution. The following figure shows the internal bar forces due to the external loads. Here, I assume that you know already how to compute the reactions, so you can just directly compute the reaction because this is the loading is symmetrical, so the reaction should be 20 kips at both supports, and you can use the method of joins to compute the internal forces. You can see here you have to indicate if it is tension and compression, because as you use this one in our computations, you can assume tension to be positive and compression to be negative. To find the vertical deflection at point A, that is delta A sub y, all of the real loads need to be removed, and a unit virtual load must be applied where the deflection value is wanted. In this case, joint E. The following shows the internal axial loads due to the vertical virtual load. So by applying the vertical virtual load at point A, you can compute the internal forces of the truss. Again, you need to indicate if it is in tension or compression, because we will be using positive for tension and negative for compression. Also, to find the horizontal deflection at A, that is delta EX, all loads needs to be removed and a unit virtual load must be applied in the horizontal direction at joint E. The following shows the internal axial loads due to the horizontal loading. If you apply the load 1.0 at E horizontally, then you can also compute the internal forces of the truss. Now place all the computed values in a table to facilitate the computation of the deflections. The value of E is left out of the table since it is common to all terms to make our computations simpler. So here we have different columns. Member, for the first column we have the members, second column the length in inches, third the area or the cross-sectional area in n's square, the internal forces of the truss due to the actual loading in kips. So you can see here compression negative, tension positive, and the internal forces due to the unit load applied vertically and small n sub y. Again, the forces up in the members, positive is tension, negative compression. Then you can just multiply these columns to get the sixth column. The column NY times capital N times the length L over the cross-sectional area. Here it will give us a unit of kips per ends. And then you can also write NX, that is the internal force of the truss due to the unit load applied at E horizontally. And then you can compute for NX and L over A. In this way, this is easier to do. And then after that, you can sum up these two columns, sum all this, all NY in L over A and NX in L over A here. The first one summation is equal to 11,020. The other one is 3,200. Of course, you can use spreadsheet or any spreadsheet to simplify your computation. It's easier to use the spreadsheet because you can just make a formula and copy it, and you can also use the internal function sum. After that, we can compute for the two deflections, the vertical and the horizontal. Of course, we need to apply the modulus of elasticity, which is 29,000 KSI. Delta EY gives us positive 0.38, and since it is positive, which is in the direction of the unit load, then 0.38 ends is downward. Also, delta EX is positive 0.11 ends. Again, the result is positive, so therefore delta AX is 0.11. No, this is not 0.1, but 0.11 ends to the right. And since both displacements are computed to be positive, they are in the direction of the applied unit loads. Before ending this one, did you know that the virtual load applied to the structure does not have any units? However, units may be used because when solving the deflection equation, one must divide again by the virtual load, including the units. Hence, it all works out in the end. So this is all about the virtual load method as applied to the deflections on trusses. Thank you for listening.